In the Sentiment Analysis app, we again have a basic chat interface. The user can send messages to the chatbot, and the application keeps track of the conversation. In addition to generating replies, the system classifies the sentiment of the current conversation. Start with a neutral exchange. If the user simply says hello and the chatbot responds politely, the sentiment is neutral. There is no strong positive or negative signal. A well-designed sentiment system should not overinterpret ordinary greetings. Now add a clearly positive message. I am really liking this new NLP course. The sentiment changes to positive. The explanation might refer to words such as really liking and to the overall expression of enthusiasm or enjoyment. That explanation is useful because it makes the model's classification easier to inspect. Next, add a more negative message. All the previous courses were really underwhelming. Now the conversation is not purely positive anymore. A good classifier may label the overall sentiment as mixed because the conversation contains both positive and negative signals. This is important. Sentiment analysis is not always about classifying one isolated sentence. In many business settings, we care about the evolving tone of a conversation. For example, a customer support chat might begin politely, become frustrated, then become satisfied after the issue is resolved. A useful system should detect those shifts. It should also explain which phrases contributed to the classification so that a human reviewer can understand why the model produced the label. This demonstration works with a general-purpose language model out of the box. It does not require us to train a custom sentiment model or write a complex prompt. The same pattern can also work with open-weight or locally hosted models, depending on the quality and size of the model. For a short chat, the token cost is usually low because the amount of text being analyzed is small. The broader point is that sentiment analysis can be built into conversational tools, dashboards, customer support systems, and social media monitoring workflows. It gives us a structured signal from unstructured conversation data. After chatbots and sentiment analysis, another foundational NLP application is speech-to-text. Speech-to-text converts spoken language into written text. In the next demonstration, the application records audio and transcribes it in real time. Once the speech has been converted into text, we can do many additional things with it: summarize it, rewrite it, classify it, translate it, or use it as input for another model. The speech-to-text example has a simple but powerful workflow. The user records speech, the model transcribes it immediately, and then the transcript can be used for a second step. For instance, we can dictate rough ideas and ask the system to rewrite them in clearer, more professional language. Consider a short test sentence. Hello, is this still recording? This is just a test. The application transcribes the speech almost immediately. This is not just near real time. With a fast enough model and connection, it can feel effectively real time. Once the text exists, we can send it into another model call and ask for a cleaned up version. The result is a practical dictation tool. Speak freely, capture the raw language, then transform it into polished written text. This matters because speech is often faster than typing, especially when we are brainstorming. Many people can explain an idea verbally before they can write it well. Speech-to-text lets us capture that initial idea, and NLP models can then help convert it into a structured paragraph, a summary, an email, or meeting notes. The cost of this kind of use case can be quite low. Short audio clips produce short transcripts, and short transcripts use relatively few tokens. Of course, cost depends on the provider and model, but conceptually, this is a lightweight application. These examples are meant to show the range of what we can build in this course. A chatbot, a sentiment classifier, a speech-to-text tool, and a text rewriting pipeline are all application-oriented examples, not abstract theory only. None of them is conceptually impossible for you to build. Some parts take time, especially the interface and the debugging, but the core model calls are usually quite compact. The next classic NLP application moves in the opposite direction, text to speech. Instead of converting spoken language into written text, we convert written text into audio. This is useful for accessibility, voice assistance, audio summaries, language learning, narration, and conversational interfaces. In the text-to-speech demo, the application uses a speech generation model through an API key. The code begins by loading the key because authenticated access is required. Then the interface provides a text input field where the user writes the sentence to be converted. The user can also choose among different voices. The provider documentation lists the available voices and usually includes short audio previews. In the application, we expose those voice options in a drop-down menu. Then the user enters a sentence, for example, "Hey there, I am new to this amazing course." The system sends the text and selected voice to the TTS model, receives an audio file or audio stream, and plays it back. Again, the important design pattern is simple. Input text, selected voice, API call, generated audio. Around that core, we can build a more complete application. For example, we could build a tool that takes a written announcement and produces audio in several voices. Or we could combine speech-to-text and text-to-speech to create a conversational assistant that listens, reasons over the transcript, and answers aloud. Once you understand the individual components, these combinations become easier to design. In a live classroom, audio sharing may or may not work through the meeting software. In a pre-recorded lecture, we would simply play the generated audio directly or show the resulting audio file. The technical point is that the text-to-speech output is produced from a small amount of code, a text input, a selected voice, and a model call. A minimal app around it may require only a little more code. Let us now recap what we have covered so far. NLP enables machines to understand, interpret, and generate human language. We have seen several concrete applications: chatbots, sentiment analysis, speech-to-text, and text-to-speech. We have also mentioned information retrieval and RAG systems, which we will study in more depth later. We also discussed industry impact. In healthcare, NLP can help organize clinical notes and research literature. In finance, it can support risk analysis, fraud detection, sentiment tracking, and regulatory review. In customer support, it can classify requests, route tickets, retrieve answers, and automate parts of the response process. Across these examples, the common theme is that language-based work becomes more searchable, structured, and automatable. At the same time, we should think critically about how we use these systems. In everyday life, many people use LLMs as translators, writing assistants, coding assistants, or general search companions. That can be valuable, but there is a real risk of over-reliance. If a tool is powerful enough to solve many small tasks for us, we need to be deliberate about when we use it and when we should work through the problem ourselves. This is especially relevant for coding. LLMs can help explain errors, suggest alternative implementations, or rewrite code. But if we always ask the model before trying to reason through the problem, we may weaken our own understanding. A productive approach is to use these tools as collaborators. Ask for a second perspective, compare alternatives, check assumptions, or review code after you have attempted a solution. There are also privacy and security concerns. Many organizations cannot send sensitive data to an external model provider. Some companies therefore build internal NLP systems or use open source models locally. The trade-off is that local systems may offer better control over data, but sometimes lower performance than the strongest commercial models. This trade-off will appear throughout the course. We are not simply asking, can the model do the task? We are also asking, where does the data go? Who can access it? What is the cost? What are the risks? How accurate does the result need to be? And how much human oversight is required? Used well, NLP tools can make us faster and more effective. Used carelessly, they can create privacy problems, shallow understanding, or unreliable outputs. Both sides matter. For this course, that means we will treat the tools practically but not naively. We will build things, test them, and inspect their behavior. At the same time, we will keep asking whether the model output is reliable, whether the data is appropriate to use, and whether the system should include human review. That habit is part of working responsibly with NLP. One way to address privacy concerns is to run models locally. Some open-weight model families can produce results that are useful for many tasks, especially when the task is narrow and the deployment environment is controlled. A model that is small enough to run on a local machine, such as a MacBook Pro, keeps the data local rather than sending it to an external API. That does not solve every problem, but it changes the privacy profile significantly. There is also a separate concern about the data used to train large language models. Many models require enormous data sets, and there are ongoing debates about what data was collected, whether it was licensed appropriately, and whether private or copyrighted material was included. We should be careful here. In this lecture, we do not need to make legal claims. The practical point is that training data, data privacy, and data reuse are all important issues in NLP. The same caution applies to web scraping. Just because text is visible on the internet does not automatically mean it can be reused freely for any purpose, especially in a commercial product. When scraping data, you should check the site's terms, legal restrictions, and ethical constraints. This will matter later when we build retrieval-based systems, because those systems often depend on external text sources. At this point, we have a working understanding of what NLP is, why it matters, and where it appears in real applications. Now we can move into the tools that make NLP tasks easier. Imagine we have a large data set of customer reviews. Each review is text, and text is messy. It may include punctuation, spelling variation, repeated words, capitalization differences, irrelevant words, and informal phrasing. We want to clean the data, extract useful information, visualize patterns, and eventually perhaps predict sentiment. We do not want to build everything from scratch. That is where NLP libraries help. In this practical example, we will use standard Python tools to clean and pre-process a review dataset. The objective is to prepare text for analysis by performing tokenization, stop word removal, and lemmatization. Then we will visualize word frequency using a bar chart and a word cloud. The workflow follows the same structure we discussed earlier. First, load the raw data. Second, tokenize the reviews so that the text becomes a sequence of smaller units. Third, remove stop words so that common but low information words do not dominate the results. Fourth, lemmatize the remaining words so that different forms of the same term are grouped together. Finally, visualize the most frequent words in the processed text. This example is deliberately modest. We are not yet building a full classifier or a production NLP pipeline. We are learning the pre-processing steps that make later analysis possible. You can think of this as the bridge between the conceptual lecture and applied NLP work. The earlier slides explain tokenization, stop word removal, and lemmatization. The notebook now turns those ideas into code so that we can see exactly what happens to real review text as it moves through the pipeline.